Okay, so today we're starting Unit 7, and Unit 7 is talking about bonding. Y'all know most of this, so let's start this with defining the different bond types. What is the most famous bond type y'all like so much? What's it called? Ionic. Ionic bonding. So ionic is the first type, and then along with ionic comes what? Covalent. What are the two types of covalent? Polar and nonpolar. Okay, and then the one type of ionic, how do we know if something's ionic? What happens with those electrons? Electrons are actually transferred. So let's say, and those of you at home will not be able to see this, but let's say I am sodium and she's chlorine. Go ahead and grab this. She's more electronegative, but she's way more electronegative than me. What's she going to do? Take it all the way. She's taking them. She's partially what, she's not, not partially, she's actually what charge now? Negative, and I'm positive. So how are we going to bond? Electrostatic attraction. So that's what ionic bonds are, electrostatic attraction. If we're dealing with polar, polar is a sharing of electrons. So say she is hydrogen and I'm oxygen. She's going to hang on. I'm more electronegative with oxygen. I'm going to pull the electrons toward me. So we're still sharing. It's an unequal sharing. Electrons nearer me make me partially negative and her partially positive. That's a polarity within the bond. That is a polar bond. Okay, nonpolar then is equal sharing because we wrote the same electronegativity. Just sharing. Sharing is caring, whatever. All right, so those are the bond types. Most important about ionic, how do you know you have an ionic? If you got a metal and a nonmetal, it's pretty much ionic. You singing in your head? Dancing in your seat? Yes. Okay. You don't like to be called out, do you? I can tell. What? It makes you uncomfortable. Okay. So before, we're going to start looking at ionic compounds. Now, I don't know if you remember this in nomenclature. What did I tell you to call ionic bonds instead of molecules? I told you to call them not compounds. Remember we were doing dimensional analysis, and I said, those aren't molecules. They're formula units. Remember that? Yeah, we did. We did that in September, actually. So nice to hear everything I teach sticks with you. It makes me really happy. So the thing about sodium chloride and any other ionic compound, they don't exist as single little things. If you've seen salt, you've seen table salt, right? They're crystals. Each of those crystals is not just one Na and one Cl. It's what we call a crystalline solid, and it's held together with what we call lattice energy. This kind of can be seen as a lattice, ladder kind of a thing. So lattice energy refers to the energy that is associated with this electrostatic attraction that exists. Okay, and it's something that we can actually calculate using Coulomb's law, which is a law that you'll learn more in physics in regards to point charges in space. Lattice energy is equal to Q over R times this really long number, and you don't need to memorize the number because we're not going to do the math with Coulomb's law. We're just going to talk about the relationship. The number is 2.31 times 10 to the negative 19th joules times nanometers. So what is this stuff? What do you need to know? What you need to know is that two things refer to this lattice energy, or actually lattice energy depends on these two things. Charge. Q and Q are the charges of the individual ions. So if I'm looking at sodium chloride, for instance, I'd have a +1 and a -1 charge. Okay? And then radius would be, we know sodium's pretty big compared to chloride, so there's our sodium. There's our chloride ion. The radius from middle nucleus to nucleus is what we put there. So we can kind of understand why charge would make a lattice stronger or weaker, right? Wouldn't a charge like sodium phosphate be stronger, a lattice, than sodium chloride? Because we have more charge, right? Wouldn't a +2+2 relationship be stronger than a +1 -1 relationship? Well, and you can see that here mathematically. The bigger the charge, the higher the lattice energy, right? Well, why is it radius? How come it's indirectly proportional? This is an indirect relationship. The only way I can really think about it that makes sense to me is, and I've done this in class before and I don't do it anymore because I actually broke the meter stick. I took a meter stick and just kind of went like that to pretend to break it, and I actually broke it. But if I broke a meter stick, it wouldn't be too hard to do. And if I took a half of it and broke it again, that'd be a little bit harder, right? And it gets to the point where I couldn't break it anymore. So the smaller the radius, the harder it is to break, the more energy it would require. And that's just because of the proximity of the nucleus of smaller atoms to each other. If I have two small atoms, the nucleus of one is therefore more attracted and closer to all the electrons of the other, and vice versa. So it's much harder to break. So it's got higher lattice energy. So for this one right here, we're not actually going to do the math. No math required. I'm going to pretty much skip it. But if we were to do it, you would plug into, let me move this so people can see. You would plug in your charges, your +2 and your -2. You'd put your radius in of that, and that constant in the formula, what was it, 2.31. Remember, it had the units of joules times nanometers, and so because this is in nanometers, we end up canceling nanometers and we get an answer of joules. This is yet to be on the AP done in math. The only AP questions I've seen are the ones that are like number 6, which we're going to go and look at here in a second. But just want to make sure that you've seen the equation. It's not on the exam. I mean, it's not on the AP equation sheet, though. You'll need it for physics, so I'm not worried. Physics will take care of it. It'll make you learn it more. So let's do that number 6 while we're talking about it. Turn pages. We're going out of order. I know. But at least you don't have to find it on the iPad. So looking at lattice energies, the question here wants to know, why does the potassium ion salts have this trend? Why does this trend exist? So first thing, when you see a lattice energy problem, I want you to jot down QQ over R. That's going to let the AP reader know you know what's going on and you know what this is referring to. So let's look at the two things. Remember, lattice energy is affected by charge and radius. Is charge going to be a reason why this has a different trend? Why the lattice energies are different? No, because they're all the same charges. All those anions are -1. So that's not it. Same charge. So that can't be the thing that's making these different. It's got to be radius. What's going on with the radius of these halogen or these halide ions? As we go across, what's happening to the radius? Bigger. Radius is getting bigger because we're going down the table there. We're more shielding. So as radius gets bigger, what happens? Lattice energy decreases. That's all you need to do. As radius gets bigger, use that equation to show it. Okay, simple. That's as far as you need to go with Coulomb's law and lattice energy. QQ over R. All right. Going back to the second problem, here we have a table of electronegativities. I'm not hung up, one of those teachers that's hung up on subtracting differences in electronegativities to tell me if a bond's polar or nonpolar or whatever. To me, that's a Chem 1 thing you do with kids because you got nothing else to do but fill in worksheets. It's not necessary, okay? Differences in electronegativity basically are, I want you to understand the trend. If I've got like potassium and something like fluorine way far apart, that's a big difference in electronegativity. So what can you tell me about the bond type? It's going to be ionic or really polar or something like that because of the difference in the electrons. We know it's ionic because metals and nonmetals are ionic compounds. I will tell you numerically what is common. Ionics, and again, every textbook you go in, this is different. Usually it's greater than 1.9. I've also seen some textbooks say 1.6. If your electronegativity difference is bigger than that, you have an ionic compound. If it's between 1.6, 1.9, and about 0.4, it's usually covalent, polar. And if it's less than 0.4, it's usually covalent as well, but it's nonpolar covalent. I don't want you even to waste your brain space on this. I'm just showing you it exists. because on some SAT2 or on some SAT or ACT Science or some college standardized test you have to take for placement, you might run into this, and it drives me insane, but it is what it is. Okay, so let's look about how we'd answer a question. Based on the chart above, or the previous page, order the set from the most covalent to most ionic character. Okay, so to order it, we do need the difference, but let's right off the cuff. NaCl we know is ionic, right? Isn't Li and H ionic? Sure, metal, non-metal. What else? We know this is ionic. Okay. HCl and HF, do we know what it is? Well, let's go ahead and find the difference there. Looking at the table above, H is 2.1, this is 3, so the difference is 0.9. Okay. What's the difference between H and F? This is, woo, Florine the floozy. She's a 4. And that's 2.1. What's the difference there? See, like that's on the edge. We know that's not an ionic compound. It's covalent, but you know, it's just silliness. So I hope it's working. Please still work. I don't know if it's working, y'all. I just knocked the mic out, so if you're still working, that's awesome. If not, I'm going to have to do this lecture again tomorrow. Okay. So we really do need to order these. NaCl, let's find some differences here. This I didn't do. You know what? I don't want to order them because of time. So basically, you would say this would be polar covalent, right? And this one would be, it's covalent, it's polar covalent. We're not calling that ionic. But if we were to rank these in order of most ionic character are the ones that have the biggest electronegativity difference. So you're ranking them from small. We don't need to do that. You guys are smart enough to do that. Small differences to larger differences. Okay. Now what is important, very important, is the determination of something called a dipole moment. This is new. This is something that's going to carry into organic chemistry for those of you who take that class. A dipole moment is just drawing the molecule and putting arrows on the molecule over each bond saying which direction the electrons are kind of shifting toward. When we were fighting over the pen, that's what I'm talking about in terms of drawing the arrow, what direction the electrons are being pulled. So HI has a Lewis dot structure of this. We're going to relearn Lewis dots tomorrow, so if you don't remember how to draw it, you will tomorrow. Are they the same electronegativity? No, they're different, so they're going to have a different electronegativity. Which one's more electronegative, H or I? I. So the electrons are going to go towards I. You draw an arrow towards I. You do a little hatch mark at the other end. Why? That's just how they do it in all the textbooks. Okay? The electrons now are closer to the I. The electrons of this bond are closer to I, giving this what we call a partial negative. That's a little lowercase delta. This is a partial positive. All that little d thing means is partial. It just means it's not really, actually, I might even be misspeaking. It might be a lowercase sigma. I don't know. We'll have to look it up. All I know is how to draw it. And it actually is an indicator in numerous areas in science of being partial charge. Okay, it's not just chemistry. So partially positive, partially negative. Got it? Lowercase delta? Good. N2. Does anyone remember what N2 looks like? It's got a triple bond. And we're going to be going over these tomorrow. Tomorrow I'm not going to be nice about you not knowing this. So we're going to whip you back into shape. Does that have a dipole moment? Does that have the ability of being a dipole molecule? No, it does not, because those have the same electronegativities. All right? So this has no dipole moment. Not going to happen. This is for Bridget, this note. At my convenience. It's not, I'm not convenienced yet. All right. The last one, CCl2F2. Don't let that scare you. You guys know how organic compounds look. What goes in the middle? The carbon. And then we're going to have all the stuff on the outside. Now, a lot of students say, how do you know where to put the F? How do you know where to put the Cl? On two-dimensional paper, yeah, it looks like it matters, but it doesn't in three-dimensional space around a tetrahedral like that. You put them anywhere, it's going to have the same result. Again, dipole moment is for each bond. So each bond has to have an arrow indicator on it. Chlorine is more or less electronegative than good old fluorine, carbon. More. So the electrons are being pulled toward chlorine. Then there's fluorine the floozy. Hell yeah, she's going to take those electrons. All right? So all our outsides are partially negative. And then the inside is partially positive. You only need to do that once. And this kind of is why when we make our Lewis structures, we're always putting that least electronegative on the central atom, because it creates, you'll see tomorrow when I talk about it a little bit more. Now, one thing before I move on to bond energy, I want to make sure you understand the difference between bond polarity and molecular polarity. So you see how all those bonds are polar, right? Okay. Let's pretend there was just F's, all F's. Just for a minute, pretend all F's. Those bonds would all still be polar, right? Okay, well, what can you tell me about the molecular polarity? The molecule having one thing in the center with all the same stuff attached on the outside? It's nonpolar. Why is that? Even though each bond is polar, there is an even pull to the F's, so there's an even distribution of charge around the entire molecule. That makes the molecule nonpolar. But we can still have a nonpolar molecule with polar bonds. I really want you to get that. Here, is this a polar or nonpolar molecule? It's polar. Why? Because F is a wee bit stronger than chlorine, right? So these partial negatives are going to be a little bit bigger. All right? So that's going to be an asymmetrical distribution of charge around the central atom. And that's actually a Wednesday or a Thursday thing. No, a Thursday topic. We'll talk about that then. We already know this. What classes of elements typically unite to form ionic compounds? Metal and nonmetal. Or don't forget good old polyatomics, right? They make ionic compounds. Because what if I did this? Are there any metals in that? No, but do you recognize that as being an ionic compound? Because there's ions in it. Okay, so just keep those polyatomics in mind. Yay, this is fun. Bond energy. Woohoo! Go bond energy. This could very well have been put in Unit 5 with all our different thermochemical equations, because with bond energy, what we're going to do today is learn how to calculate the delta H of a reaction this way. What were the ways we calculated delta H? We had calorimetry. What else? Big Mama, flippy thing, stoichiometry, right? And bond energy. The reason the textbook puts it in this chapter is because it's about bonds, and that's what we're talking about today, are bonds. What these numbers are, simply enough, this 259 right here is the number of kilojoules per mole required to break CS. It's also the amount that's released when CS is made. So all these bonds have energies associated with them. I'm going to give you a couple days to memorize it. I'm just kidding. I like the look on Haley's head popped up. I'm kidding. You don't have to memorize it. You'll always be given what you need. One thing to make note, C double bond O is 745, but see, that's an asterisk. I know it's hard to read. You come down here, the C double bond O specifically in CO2 is actually 799. So if you're given CO2, you use this one down here. Any other C double bond O, like in ketones or carboxylic acids or esters or aldehydes, you'd use that one. Okay? And we're going to review all those compounds before the end of the year. Don't fret. So let me show you how to do this. This is fun. Y'all are going to like this. To do these problems, you just need to remember the following. Bonds broken minus bonds formed. Yay. Okay, super simple. Now, I just want to tell you, this is actually Big Mama. And I know it doesn't look like Big Mama, because what is Big Mama? Don't write this down. I'm writing this down. Big Mama is really products minus reactants, right? I'm about to erase this, so don't write it down. Products minus reactants is really that minus that, correct? Bonds broken are those minus those. What? Why are we doing that? Well, it has to do with the sign thing, and this is actually trying to help us. If I were to do Big Mama like it is, I'd have to say, okay, products minus reactants. Bonds formed, when bonds are formed, energy is released. So what would I have to do to all those charges? I'd have to make them all negative. So I'd have to make them all negative, and then products minus reactants. Here, these are actually broken, so to be broken, we put energy in. So these I'd have to leave positive. And I'd have to subtract them, though. How confusing is that? That's ridiculous. So instead of making us suffer, somebody came up with, oh, just do bonds broken minus bonds formed. By doing that, the signs are taken out of it. All you have to do is leave them all positive, figure out what's broken, and figure out what's formed. So when we're breaking here, what are we breaking? We're breaking 4 C to H bonds, right? Okay, so that's 4 times, go ahead and find C to H on your chart. I've got these written down. 4 times 413. And we're also breaking 2 O to O's, right? Because they have a coefficient of 2. So it's 2 times 495. So that's bonds broken minus bonds formed. We're forming 2 C double bond O's, but that's in CO2, so we got to use that 799 at the bottom of the table, plus how many H's? How many H's are we breaking? That's actually not that's a real question. How many? 2, but we got 2 in front of it, right? So how many are we breaking? So 4 hose are being broken. 4 times, she's not fluorine. She's not the floozy. 467. Okay. And the unit on all these numbers I'm just randomly putting in here without thinking are kilojoules per mole because it says on the top of the table. Okay. All right. When you put those all in your calculator, you get -824 kilojoules per mole. So now we're going to look at this, and we have to know your Lewis structures. You have to know that that's a triple bond, or you won't know what to use. And again, you'll know after tomorrow. H2, we have 3 of them. Oh, they're single bonds. And then this guy, does anyone remember what ammonia looks like? And it's not important for this exercise, but there is a double bond there. But again, we have 2 of these. So we're breaking 1 triple bond, bonds broken, 1 times 941, plus 3 times 432, bonds broken, minus, how many NH bonds are we forming? There's 3 in the molecule, but I've got 2 out in front of it, so 6 times 391. Bonds broken minus bonds formed. So when you do it, you get -109 kilojoules per mole. Okay? Don't change the page yet. Close it back. Questions on this? Okay. For a purple sticker. First one, don't change the page yet. The first one to complete the next problem and bring me the answer gets a purple sticker. If it's correct, go. You need to be prepared for class. You don't have a calculator. Sorry, you can't get a purple sticker if you don't come to class prepared. Jacob, if you're listening to this lecture, everyone is actually really excited you're not here because they feel they have an equal shot of getting the purple sticker. Just so you know. But I miss you because you yell out the answers. Hope you're feeling, oh no, you're at Live Oak, never mind. Okay, good job. We have a new winner. So what y'all are messing up on mostly, well, I'm sure you all got the 12 C to H's, right? A lot of you are probably missing the 2 C to C's right here. And that is 2 times 347. And then you've got 7 O to O's at 495. That's broken. Minus. And then here, another thing people are messing up on is this. This is 8 C to O's at 799 because it's carbon dioxide. And then we're breaking 12 O's in this example, 467. And so when you do that, broken minus formed, you get your delta H of your reaction as negative 2881 kilojoules per mole. A common thing that, not a common, about 3 years ago on the AP, I actually graded this question. They gave you the delta H of the overall reaction and wanted you to solve for the bond energy of one particular item. And I believe it was nitrogen. I think it was N to N. So you'd basically do the same thing, but you'd make it X, one of them X, and you'd solve the same way you did in the last unit. Remember doing those problems where we put an X in? It's important to realize that bond energies are always positive. How do I know that? Look at the table. Look at the data that's given to you. If you're given a table with some bond energies and you have to find another bond energy, why would you solve and think a negative is okay if all the rest of them are positive? Okay, so watch for stuff like that, because that was a huge pitfall on that particular problem. All right. We are done for the day. Hopefully this taped. Please.